continue. Share my screen. There we go. Okay, here we are, learning the material. The quiz questions that we just had are, I would say, typical of the kind of questions I'm going to ask about the material on the final exam, right? Somebody sent me a nice polite request asking to see a formula sheet for the final exam so they would have some time to, think about what else they want to put into their head. And that's a good idea. And I've come close to finishing that. My idea of what to do will be to show you guys that on Monday, say, and then you can ask me, can you add this? Can you add this? I'm fine with that. I'm happy to do that, and then you'll have it a couple of weeks in advance, and you can know. But really, I think I cannot see myself saying use the 5-point center midpoint rule for finding this derivative. Like that's not that useful, particularly if the formulas are on the formula sheet. It's like, okay, so you can plug in the numbers. That's not that exciting. So this type of question where it's like, can you did you understand what Richardson extrapolation is? Can you do it on h by 3 instead of h by 2? I mean, the next obvious question is to have it, h by 4. And you're like, okay, try again, sort of thing. So, and then another question too, is just a method of saying, do you sort of understand what these rules are doing? How they are similar and different. Okay, so those are more typical, particularly the Richardson extrapolation one. Okay, so the formula sheet, Richardson extrapolation I wanted to say about, and I think that's all. Are there questions for me before I start with this material again? Yeah. Yeah, so this is a question about, how comprehensive it's going to be. Now, clearly we've already had some questions on the first part of the course, and we haven't on the second part, so I would say it'll be weighted more towards the second part of the course. And then the usual math answer is, of course, some of this stuff in later parts of the course does rely on that stuff from earlier parts. So I can get 2 birds with 1 stone model, right? So yes, it will. And I will actually, I do not have yet a final exam. As soon as I actually have the final exam, I will actually give you, and I'll tell you how many questions, and I'll give a bit more direction once I have that. Yeah, we're early in the exam period. I think I forgot. I think we're 2 days after the last class or something. So we want to sort of get going before exam period starts. Yeah. Other questions? Yep. Let's see if I don't know if I have let me see if I can just find those for you. Sure. Let me just, I would just, oh, that's all of the solutions. Hang on. So there's question 1. You try to make an OH squared approximation. That means you need to get rid of the OH term. And you take an N and an N by 3 approximation as requested. And then you figure out the algebra necessary to eliminate that term where I said cancel out. Okay, this was part 1 of the 2-part question, right? This was a signed question, exactly. And then the question actually asked you to go for the OH cubed approximation, which you have to do that in the next step, right? I just did the first part, right? Okay, so that's the answer there. And then this one here, you do the trapezoidal approximation, you do the midpoint approximation, that gives you the function values you need to do the fifth approximation. Okay. Other questions? Okay, let me just, because I'm in this kind of a mood. Let me just point you to the fact that something interesting is happening right now. I don't know how it's going to play out, but there is a person His name is Yitang. I believe his last name is Shang, but I might not have that right exactly. Anyway, he a number of years ago, he made substantial progress on the twin primes conjecture. So the twin primes conjecture was a long outstanding problem, 300-400 years. Nobody had been able to prove the twin primes conjecture, which basically says that there's infinite pairs of primes separated by one, like 13 and 17 and 19, right? That you find one even ginormous prime that are separated like that, and that there's infinite supply of these things. Nobody knows whether that's true or not. It has not been proved, and it's anyway. So he made a major breakthrough on this. I think it was maybe about 10 years ago, if I recall. I can't remember. Time goes by really fast, but it was in the kind of 5 to 10 years ago. He made a huge breakthrough. And he didn't manage to prove the twin primes conjecture, but he did manage to find a bound. Like, for sure, there's infinite supplies of primes that are this distance apart. I think the number was like 40,000 or something. It wasn't 2, but at least he had a technique for finding that there was a bound. Okay, and as soon as that happened, a bunch of other people learned how to do that, and then now the bound is down quite low, right? People have been chipping away at it, the bound has come way down. And he was also not sort of on anybody's radar. He's kind of a sort of low profile person at not a major institution. So it was, and he was in his 50s when he did that. So it's a really interesting story. He's sort of not come out of nowhere, but he's clearly been working away and whatever. Now, I saw some reports recently that he has made progress on with the Landau-Siegel zeros problem, which it doesn't matter. It's spell it right. It's related to the Riemann hypothesis. Yeah, right. Okay, this is major, right? So he is apparently there's been reports out that he has published something that it would indicate a major step forward into providing a proof for the Riemann hypothesis, which is a hugely famous, outstanding problem, and that is about prime number distribution. And I saw that about 2-3 weeks ago, and I was like, okay, this is being reported sort of in a Chinese blog site, and I didn't really understand whether it was who's looking at that and whether it's true. Anyway, I did find out today that Terence Tao has spent a bunch of time reading through the paper and has raised some concerns, but has said they may be fixable. Terence Tao is like probably the most famous mathematician currently working. He's at UCLA. This guy is out of the gate, learned all of calculus by the time he was 8, that kind of a person. So yeah, Terence Tao has spent time on it. That's one major step right there. And then it looks like, so this guy now at this point, he's now 67. Like, this is unbelievable. Really, it's extraordinary. You should sort of follow this. It's totally cool. No, that, and I saw a little quote from him. Somebody asked me if he's going to retire. He goes, no, not retiring. I couldn't live if I didn't do math. That's it. Okay. So this is somebody who's doing things for maybe perhaps the right reason. All right, follow it along. It's like a soap opera, but more interesting, way more interesting. Okay, here we are. We are talking about, what were we talking about? We are talking about Euler's method, and we had a analysis of the global error. Let's just scroll back and say what that was. We didn't really do the analysis ourselves. We kind of relied on the textbook. Let me just find where that equation is. Hang on. Here it is. Here. Oh, that's the convergence condition. Oh, here it is. Here's the error bound right here. We had this, which was a global error bound, and it's an OH situation, right? That's right there. That's an H. Okay, so it's an OH, the global error, and then so now we have an idea, and we're going to look at instead what we're going to call this local error. That's partially because it is difficult to actually analyze some of the more complicated methods and figure out what the global error actually is. So, we are gonna look at local truncation error and order. And what does this mean actually? Before we stopped last time. So let's define what is local truncation error. It's a little bit, difficult maybe to wrap your head around, but it is equal to the amount by which the exact solution fails to satisfy the approximation, which is a difference equation. Let's get backwards. Okay, but what we're gonna do is we have a method of making an approximation. We're gonna say by how much does the exact solution fail to satisfy this? I have, we think this is in the textbook, it's in the brain, this is in section 5.3. Okay, so here's Euler's method. That's what that is. We have an initial condition, and we have an update rule. And that H is our step size, and we have a function that depends on the independent variable at time I, or we call it time I, the independent variable at I, and then the previous approximation. Here is our I is going from 0 to n minus 1, where we're using n into that. Okay, we're gonna say that this type of, well, this method is, we're going to call it order P if exact solution minus our approximate solution, where I take the approximation and apply it to the exact number. So this is the exact number from time I. I'm going to apply the approximation to the exact solution at time I, and then I'm going to take the exact solution for time I plus I and see how much is it. You see what's different about this? If we're not subtracting yi plus 1 minus wi plus 1. We're subtracting the exact solution at time I plus 1, and from that we're subtracting the calculation we would make, but we're using the exact solution at time I. This is why it's a local error. It's just like, what goes wrong if I know exactly at time, I know the exact answer at time I, and then I get and I know, and I use that to approximate the next time step, and then I subtract the exact answer. It's just that local step, like how badly is it gone wrong in one step. Okay. That is of order P if this thing is OH to the P plus dot. We call it order P. So we can do this with Euler's method. For Euler's method, what we have is that phi is that function T I Y I is simply that thing that's right in the differential equation. We can take a look at this guy here, which is, I'm going to now label it like that, but I'm trying to make sure that y sub I plus 1 means function evaluated over time, T I plus 1. That is I plus 8 y prime at T I plus x squared over 2 y double prime at some. Okay, this right here is scalar. Then I can subtract y minus y I. That's then equal to 8 squared over 2 double prime. Try double prime outside. Point being that this number here is a 2. So Euler's method is order of that. P is equal to that. Because this is a 2, and the order here is H to the P plus so P is the order. So we have here the Euler's method is order. Okay, what does this mean? This means that the error per step, this is implying that the error per step, we looked at the local truncation error. So the error per step is proportional to the square of the step size. Why is that being square? Square of the step size. That is the step. Square. Square of the step size. The global error was 0.8. If we look at the local error at 4 that does not guarantee global error, but it is in this case. Okay, so there's a demo in MATLAB that you can run, in Canvas that you can run for your run. And it applies Euler's method to this initial value project. So if we're looking for a solution over this interval, we are using this as our initial condition. This is telling us that y at 0 is done. Because that is our initial time, 0. So we're going to go from 0 to 2, and we have an initial condition at 0 on our function as well. So we're going to do this demonstration. The exact solution is here. You can find, just going to outline for you how to find the exact solution to this suggestion. First of all, you can check it without finding it. You can take that and take the derivative of it, and then see if it equals to that. Right? You plug the y in here, you plug the y prime in there and see if it works. So first of all, you can check the solution. That's step 1. The other thing you can do is here you've got dy by dt, and that is 1 plus t over 1 plus y. And then you can separate this one. dy times 1 plus y is equal to 1 plus t. And then you can integrate those back. This is actually easy to solve. Positive to see how that's solved. Okay, so you do that. You have an exact solution then that you can plot, and then you can run Euler's method and start it here. And you see actually it's pretty good. I mean, the blue line, which is mostly on top of the red line, you can't see very well. They're giving you the same solution. So the blue is like the exact solution plot, and then the red is the Euler's method, which of course is the discrete one. And then you can see that the error continues to increase as you do more and more steps. That is totally difficult. And then you see here the global error. Now this is where you define you take 40 steps, you take 80 steps. This is increasing on that side. And you'll notice here that what's happening is this is decreasing by a factor of 2. A factor of 2. So it's halving, decreasing by a factor of 2. And at the same time, this thing is times 2. So this is 0.8 behavior. And that's exactly what we found in global, when I told you the global error, because that is happening, that already happened. That's the global error. Okay, Roger Euler's method is extremely simple, right? It's based on a transient line approximation. Yes, and it's not used in practice. Not accurate. Questions? Good. Let's just now take a look at Google section 5.9. And you can see how we can use Euler's method on a slightly more complicated system, the higher order equations. Okay, so we have so far looked at this situation. Y prime is some function of independent variable and y. So let me just give an example of that, like y prime plus 2y equals 0. So there's an example. We've looked at these. These are the first orders. It is a first possibility that we can have something that looks like this. Like that. That would be a second order, because we have a second derivative. So this is second order. And the goal here is that we can realize that if we have one of these second order guys, we can transform it into two of these guys. So after we know how to solve the first order one and the second order one, we will solve the problem from two to four. Yep. That's one of it. The functional equation, we will set up 10 first order differential equations and solve them all, and then we will depend on one. That's what this question is about. How to take a higher order system and transform it into a system of lower order one. First, we're going to take a look at solving a system of first order equations. So we're here, something like this. Y1, this is just an example, is let's just say some function of t and y1 plus prime t y2 plus e to the t y2. Okay, so now instead of y1 just being a function of t and y1, it's also a function of y2 and y3. This is time like that. So that derivative, and then this one y2 prime would similarly be some sort of function of y1, some other function of this would be a third order. This would be a system of three, and they're coupled. They both seem to be as they're coupled. So this is going to be some function of three, let's put it like that. Four, three, nine, it doesn't matter what the actual functions are, but the important thing to notice is this derivative, y1, is a function of y1, of y2, and of y3. This derivative is a function of the independent variable t, also of y1, y2, y3. Okay, so you're coupled. This is a system. The system of differential equations of third order. Okay, this is the same idea, perhaps as this is the same idea of being like this in the world. So there's an equation, right? And then saying, oh, hang on, though, here. system equation. Right? So, one equation, that was our sort of our third one differential equation, and now we're here, differential equation. So we've got n of them. We've got n of them, and we've got n plus one. And we've got the initial variable plus the other variable. Each one of them has an initial condition. So y1 at time A, when the clock starts at time A, we'll have an initial condition. The function y2 will have an initial condition, so there's n of them. And in order to find all of these different functions, now we've got n differential equations. We want to find n functions. We do this math-equation model using exact vectors. So everything actually looks exactly the same, but it is now written out in vector notation. So our unknown function, which in fact is not just a single function, but we call it like this, y of t. What we're meaning when we do that? I mean, it is. Okay, so this would be based on three. First, and then we have the right hand side, and this is the vector, independent variable not a vector, and then that looks like this. That's done. So this is just writing the same thing out again using vector notation, so we can have the file of them. Again, then we would have the initial conditions. The initial conditions in this case. We have sort of an example. We have an example here that we can put here. Let's see if I can manage that. It's going to be the next one is the other one. When we write this thing in vector notation, we have that y prime of t is vector of all these functions that is this here. And t still goes between 0 and a and b. And we have a vector of and this guy y prime to like this. Now that's okay, so we have exactly the same in the vector notation. Okay, I think that's a great place to stop. We're gonna come on Monday and we're gonna try to apply orders method to that system, and then we're gonna learn how to make the higher order ones into these guys. Have a nice weekend, guys.